All right, so when Jeff talked, he talked about how the ancient Greek astronomers had figured out that the universe is full of stars, which were like our sun and things like that. But by the Middle Ages, we got ourselves pretty well confused again. And so then there was this model which everyone thought the universe had the Earth at the center of the universe and everything in orbit around it. But at around the 1600s, Galileo and Kepler and Newton provided observations and theories and some equations that basically took that model and kicked the Earth out from the center of the universe and put the sun in the center of our solar system, which was in no particular special place, and the Earth and all the other planets were in orbit around it. And once this model became all the rage, then it became incredibly important to measure the motions of stars. Because measuring the motions of stars would give us some proof that this model is actually the right way to think about the universe. So what kind of motions can you measure? Well, the first thing people wanted to measure was parallax. And you can see what parallax is if you hold your finger up at the end of your arm. This is audience participation. And I haven't had so much theory that I don't know what finger you're using. So if you hold your finger up and you close one eye and you look at where your finger is relative to something in the background, if you're at the bar, you can use me, if you're whatever you want to use. So figure out where your finger is and then keep your finger still and switch eyes. And you'll see that where you think your finger is moved. And the reason that happens is because your eyes are not in exactly the same place on your face, and so there's some angle between them when you look at your finger. And you can use the apparent motion of your finger to measure where your finger is at the end of your arm. And stellar parallaxes work the same way, only instead of using the distance between your eyes on your face, you can use the entire diameter of the orbit of the Earth, and you can use the same motion of a nearby star relative to the background, and you can measure the distances to the star. So parallax is important because just the observational fact, just measuring the parallax of the star, is proof for this idea that the Earth goes around the sun. And then you can actually use that measurement to measure the distances to the star. The other kind of motion that people wanted to measure were called proper motions, not because they had good table manners or they knew how to fill out paperwork or anything like that, but because the stars themselves were moving. Because once people picked the Earth out of the center of the universe, they realized that there was no need for that crystal sphere with all the stars stuck on with Velcro or Elmer's glue or whatever. But in fact, they realized that the universe must be full of stars at all different distances in a very, very big or maybe even infinitely big universe. And so measuring the motions of those stars was important to show that that's really what was going on. So, in fact, measuring the motions of stars was like looking for the Higgs boson of its day, or measuring the human genome, right? This was a big deal. It was an important measurement that people wanted to make in order to prove some model for how the universe worked. And like all such measurements, it was also really, 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 really hard to do. Okay, so this idea that the fact we had a solar system with the sun in the center that happened in the 1600s. And in about 1716, the astronomer Edmund Halley, he of the 76-year comet, measured the motions of 3 of the brightest stars in the sky, so Sirius and Aldebaran and Arcturus, which are stars you can see if you go outside at night at various times of the year. And he measured where they were, and he looked at where they were in a tabulation from someone named Hipparchus of Rhodes. And Hipparchus of Rhodes made his measurements in the year 300 before the present. And Halley showed that those 3 bright stars had moved. They were clearly in a different place in the year 1716 than they were in the year 300 AD, BC. So that's great. Halley measured a proper motion. He showed that the stars were moving independently of the sun. But it took 2,000 years between Hipparchus' measurements and Halley's to actually make that measurement. Proper motions are very, very tiny. The stars move a very, very tiny amount every year. So they needed 2,000 years of motion before Halley could make that measurement. And parallaxes were just as hard. Even though people started trying to measure them as soon as better happened while proper motions were still cool to measure the first time around. And that was photographic plates. So photographic plates are great for 2 reasons. They're big. And so instead of measuring the position of a star relative to some wire in the eyepiece or something, you could actually take a photograph and you could measure the position of the stars relative to lots and lots of background stars. Now you can do a much, much better job. The other great thing about photographs is that they're permanent. So you can take a photograph of something you want to measure, and then you can wait. You can wait a week, you can wait a month, you can wait a year, or you can wait a decade. And you can go back and you can take another photograph, and you can put those two right side by side, and you can measure how much the star is moving. Which is a much, much more powerful way to do it than just squinting through an eyepiece. So then people could actually measure proper motions for more things. And sure enough, in 1916, somebody by the name of E.E. Barnard at a place called Gerke's Observatory measured the proper motion of the fastest star, the star with the speed record for moving across the sky. The star he took a photograph of in 1916, he compared it to one taken in 1888, and sure enough, the star had moved. And so he managed to make a measurement, not now needing 2,000 years, but he still needed 28. And so the business of proper motions went on using photographic plates, but it was hard work. And even with the best photographic plates, and even with the whole length of a career, you couldn't really measure the proper motions for all that much. You could measure the proper motions for stars that were most nearby, or maybe the most exotic, moving the fastest. And so once the novelty wore off, most people moved on to other exciting things like figuring out how stars could work, or figuring out or realizing now that people had measured the fact that galaxies were very, very distant, that the universe was expanding, and the infant science of cosmology became the hit thing to do. And so by the time I was a graduate student, proper motions were things that were measured by people with a lot of patience, with outdated equipment, and who didn't mind waiting a couple of decades for a result that wasn't nearly as glitzy as, say, how much mass is in the universe. And all the celebrity professors with sports cars who had license plates like Big Bang and Redshift, they were cosmologists, they didn't measure proper motion. So what happened? How did proper motions get cool again? And the answer is that all those things that made proper motions hard to measure, the technology started to catch up and make it easy again. So one of the things that makes it hard is that the atmosphere takes an image and makes a big fuzzy blurry blob out of it. And if you have a big fuzzy blurry blob, it's hard to measure where that blob is. And that means it's hard to measure and see that blob change position as it moves. So you like to fix what the atmosphere does and make that blob blurry. So one of the things that happened is that something called adaptive optics came along, which lets you correct using a whole bunch of mirrors and lots of computers what the atmosphere did and go back and give you a nice tiny image that you can measure very, very accurately. And people started to use that to measure the proper motions, not just of nearby stars, but stars near the center of our galaxy. And they discovered that they were whizzing around at incredible speeds, and they realized that they could measure their orbits if they whizzed around something very, very heavy near the center of the galaxy. And with more observations, they got better and better estimates of the orbits, and they realized that that very, very heavy thing was very, very, very small. And as they measured the orbits using proper motions better and better, they got that very, very heavy thing in such a small space that the only thing it could be was a black hole. So that's cool, right? Proper motions now are actually measuring some of the most exotic sort of realms of physics that we know. They're actually showing that black holes exist, and that there's 4 million solar mass black holes in the center of our galaxy. Another way to get around what the atmosphere does, making big fuzzy blobs, is to go out of the atmosphere. And so the European Space Agency launched a satellite called Hipparcos, after Hipparcos of Rhodes, who made those measurements, 300 BC, that Halley used. And so they got a satellite above the atmosphere, and it could measure the proper motions of millions of objects. And so now, instead of just seeing the proper motions of a few special stars, we actually could take a census of what the galaxy was like. What are all the stars like? Where are they? How are they moving? So now we can actually really learn about our galaxy, a much cooler thing to do than just to sort of see your own neighborhood. And the other thing that happened that makes proper motions cool again is that cameras, that the digital detectors, like the ones in your cell phones, got really big. Or, as Robert pointed out, you could actually put lots of them all together and make a really big camera. And so now you had something like a photographic plate, which is big and which is permanent, just like your photographs on Instagram. We can save the images from astronomical cameras, only much, much more sensitive than a photographic plate. So now we can measure the proper motions of things which are really, really far away. And so the project that so many of us are here to have a meeting for this week, the Large Synoptic Survey Telescope, is going to be just about the biggest and baddest camera you could possibly imagine, and the biggest and baddest camera that's going to be mapping the stars. And with the LSST, we're going to be able to measure the proper motions, not of things near the sun, but even further away in the center of the galaxy. We'll be able to measure proper motions and measure the orbits of stars near the edge of our galaxy, and use them to weigh our galaxy and have some idea of what our home in the universe is like. We'll be able to trace stars back and rewind their migration through the galaxy and trace them back to the clusters where they were born, or find stars which were actually born in other galaxies and were swallowed up by our own as it grew in mass. So all those are pretty cool ways to measure, to learn about the universe, and that makes proper motions cool again, as many of the people here in the room will show. So stay tuned for results in when the LSST happens.